G'day folks, I get a lot of questions about hybrid orbitals, a lot of confusion. What are they? Where do they come from? How do you make them? How do I know what sort of hybrid orbitals I've got? So let's break it down. Let's just talk about a carbon atom, and we'll compare a carbon atom to a carbon that is in a molecule. Because as soon as a carbon atom is in a molecule, it doesn't have atomic orbitals anymore. In principle, it has molecular orbitals. Now, valence bond theory uses something called hybrid orbitals. So it's not quite the same as molecular orbital theory. It's its own theory, but if you like, it's a stepping stone to full-blown molecular orbital theory, which we'll talk about another day. For the time being, we're talking about hybrid orbitals, and hybridization is something that comes out of valence bond theory. So if we were to start with a carbon atom, so a carbon atom, in other words, it is not in a molecule. So it has atomic orbitals. Well, what sort of atomic orbitals does it have? Let's just focus on the valence shell, because the valence shell is what is involved in the making of bonds and the breaking of bonds and so on. We know that a carbon atom has 4 valence electrons. Its electronic configuration is 2s2, 2p2. But what are the atomic orbitals? We have 1 2s atomic orbital, and we have 3 2p atomic orbitals. And you might remember these as, what have we got? We've got the 2px, the 2py, and the 2pz. So these are the atomic orbitals in a carbon atom. As soon as a carbon atom is in some sort of molecule, these things, they turn into something new. They turn into a hybrid form of what they once were. That's why we call it hybridization. If you think about a labradoodle, for example, a labradoodle is a hybrid between a Labrador and a poodle. So we could, in this case, we've only got 2 things. We've got s orbitals and p orbitals. So we could hybridize these things. So we could get an sp orbital. Or perhaps you could do it in different combinations. You could take one of these 2s atomic orbitals and hybridize it together with 2 of these 2p atomic orbitals. Because it's an s, a p, and a p, we call that sp2, where the 2 is superscript. There's another possibility. We could get all 4 of these things hybridizing together. So it would be an s, a p, and a p, so we would call that sp3. So in this case, if we're talking about a carbon atom in a molecule spelled like that, then you would get these different sorts of orbital situations. Now, one of the golden rules is you don't lose any orbitals. We start with 4 in a normal carbon atom. A carbon atom in a molecule, you finish with 4. You still have 4 sorts of orbitals. You might have 4 hybrid orbitals, or you might have 3 hybrid orbitals, plus one of these original orbitals that didn't get involved in hybridization. So let's think about the different possibilities. So if we've got sp hybridization, that's mixing an s and a p. So you're mixing 2 orbitals together, and so you finish with 2 orbitals. So you get 2 sp orbitals plus 2 p orbitals. Let's try that one more time. So you have 2 sp hybrid orbitals plus you still have 2 p orbitals. All right. What about if you've got sp2 hybridization? Well, where would that come from? That would come from mixing an s and a p and a p. So you start with 3. So you finish with 3 of these things. And you've still got an unhybridized p orbital still hanging around on that carbon atom in the molecule. There's one final possibility, and that's where you've hybridized all 4 of these things here, and you end up with 4 sp3 hybrid orbitals. We've used them all, so we don't have any leftover p atomic orbitals. In the next video, we'll talk about what these things look like.